Hi everyone, here are your notes for section 4.5. So now we're going to really start getting into the meat and grit. I just made that up. That was not very good. Sorry guys. Now we're going to get to the fun stuff of trigonometry functions. So we're going to be looking at a whole bunch of different properties today. And the cool thing is you're going to have to memorize all of these. Yes, I mean, technically you'll have your notes in front of you, but because all of your assessments are timed, you're going to want to have these memorized so that you can get through your assessments in the appropriate allotted amount of time. So get these in your head. All right, so let's start chatting away about ratios in the unit circle. So on the example 1, we have in the sketch at the left, theta is in standard position with point P at x comma y, and let's say that it's a point somewhere on the unit circle that corresponds to theta. So complete the following terms in x and y. So if you guys remember, we kind of already talked about x comma y being the same as cosine theta comma sine of theta, right? Because cosine is adjacent. What's the adjacent axis to our theta would be x, and then opposite would be your y when we make that right triangle, right? I guess my right triangle would be right here with my reference angle. But anyways, so sine, let's think of sine being y, right? So it's going to be y. Cosine will always be your x, and tangent is opposite over adjacent, which really is the same as, sine theta over cosine theta. So it's going to be y over x. Cosecant's the reciprocal of sine, so that would be 1 over y. Secant's the reciprocal of cosine, so 1 over x. Cotangent's the reciprocal of tangent, so x over y. Okay, so think about your x and your y no longer as x and y, and think of them as cosine and sine. Okay, so now we're going to do a little sidebar here so we can start talking about the domain and range of trig functions. So you can either just watch this or put this in your notes, that's up to you. But just for where we have some context about where these come from. So here I'm going to make a unit circle. Ooh, I can do better than that. Yeah, it's a little bit better. Okay, so unit circle. Remember we have 1, 1, negative 1, negative 1, right? So it's 1 unit all the way around for your radius. So when we're talking about the domain, let's first start with the domain of sine, because I think that's the first one that's listed there. So the domain of sine of theta. So sine of theta, remember if we think about this as being some point x comma y, if I think about theta as my angle, right, so my angle theta, well, what numbers could I possibly go? Well, I could do 0 to 360, but then I could do a whole nother rotation and get to 270, and I could do a whole nother rotation. I can keep doing rotations and keep doing multiple infinite number of thetas. I could go in the negative direction, right? Couldn't I go this way? Negative 360 all the way around. So because it's periodic and I can keep looping and looping around in my revolutions, the domain of your sine is going to be all real numbers, right, from negative infinity to the infinity. Same thing applies with cosine. Cosine, it's the same concept. If we think about what I can put in place of theta, I can put any number for my degree, or in radians if we're thinking in radians, right, depending on whether I'm going positive or negative in my rotations. Okay, so my domain for sine and cosine are going to be your all real numbers. Now if we think about the range, so I don't know if you want to get that in there, I'll put it here for now. Oh wow, bad infinity sign. It's because my fingers are cold. If we think about the range, so your range would be the output, right? So your output is going to be, well, what's happening? When we get that out, we're going to get something on my unit circle, right? Well, I can only get something in between 1 and -1 for both my sine and my cosine, right? So my x is cosine, so my x is only going to be going from -1 to 1, and my y is only going to be going from -1 and 1. So those will be your ranges. So your output is your input is your theta. What thetas can I put in? I put any infinite number of thetas in there. But my output for my x's is always going to be from -1 to 1, and my output for my y's is always going to be -1 to 1. So if we go back to this table here, scroll this down. So is there any undefined parts of sine? No, there aren't, because technically sine theta is just kind of like having sine over 1, and you have 1 in your denominator, so there's no constrictions to your denominator, so there is nothing that makes it undefined. So our undefined is -infinity to, or sorry, I'm on the wrong part, none, no, nada, no undefined parts. My domain is -infinity to +infinity, and my range is including -1 to 1 inclusive. Same thing for cosine. So again, that's just like having it over 1, so there's no constrictions to my domain or my denominator. So -infinity, -infinity, and then -1 to 1. Okay, so now we got to get to our tangent. So let me, I don't know if I erase it. Hopefully you guys have that. Rewind if you don't. So now let's think about tangent. So tangent of theta is, remember we said it was y over x, which really is the same as sine theta over cosine theta. So what's in my denominator? My denominator is cosine of theta. So if we think about my unit circle, okay, so here we're at 0 to pi, depending on where we're starting or finishing. Here we're at pi over 2, here we're at pi, and here we're at 3/2 pi, right? So if I have my ordered pair of x comma y, and cosine is my x, I cannot have 0 in my denominator. So where is my x? 0. Well, my x is going to be 0 at 0, 1 and at 0, -3. So I am now undefined at my pi over 2. If I add a pi to that, that gets me to 3/2 pi. If I add another pi to 3/2 pi, that's going to take me back to the top of my x-axis or my y-axis, which will get me undefined. Adding another pi would get me to another undefined, adding another pi, right? Because a half circle we know is a pi, right? Adding another, adding another, adding another would make it undefined. So if we go back to our chart, again, I apologize, I know that the first part's already deleted, but we're at the tangent now. So we are undefined on the tangent, and we're undefined at, oops, I'm in highlighter mode, theta equaling 1/2 pi and at 3/2 pi, but then at each variation of that, right? So I can keep adding a pi, I can keep subtracting a pi, and I'm going to get to undefined parts of that. So how do we write that out as the domain? So my theta cannot equal 1/2 pi plus pi times some number k, where k is an integer, right? Because I can multiply it by any scalar of pi, right? And that would get me to that undefined part on my graph. So what's my range? Well, it's going to be everything up. So if we think about it, my graph, right? So what's my range? So it's going to be everything up to here, and then everything, whoops, everything on this side, and then everything on this side, right? But not including these guys. So my range can't include, or it can include, it's going to be everything gapping between -1 and 1. Right? So we're going from -infinity to -1. And then there's that gap there from 1 to +infinity is going to be my range. Okay. All right, then cosecant, remember, is the reciprocal of sine. So reciprocal of sine, 1 over sine of theta. So now I have to think about, well, where is my sine of theta equal to 0? Because I cannot let it be equal to 0. And that's going to be at 0 and pi on my y or my x-axis. So how do we write that out? So theta cannot equal pi k, where k is an element of integers. And my range here again is going to be negative infinity to negative 1, union 1 to infinity. Secant, remember, is your reciprocal of cosine. So that's 1 over cosine. So where is my cosine? 0 again, well, it's just going to be the same as the tangent. So at pi halves, 3 half pies. So how do we write that out again? So theta cannot equal half pi plus pi k, where k is in the integers. And again, my range is going to be negative infinity to negative 1, union 1 to infinity. And then cotangent is the reciprocal of tangent. So that's going to be, instead of sine over cosine, it's going to be cosine over sine. So where is my sine? Going to be 0. It's just going to be the same as the cosecant. So 0 and pi. So theta cannot equal pi times k, where k is some integer of z. And then for this case, my range is going to be all real numbers. Okay. All right. There be that. Oops. Okay, pause if you need to. If not, let's move on to periodic functions and finding exact values. Okay, so periodic functions. The behavior of the sine and cosine repeats after one revolution. This repetitive or cyclical pattern is called periodic. Therefore, one cycle for sine and cosine has a period of, now let's think about this. Your sine and cosine has a period of 2 pi, if we're talking in the mode of radians. While the tangent function, right, so tangent, oops, that's not what I wanted to do. Tangent is only working from 1 pi, right? So my tangent only has 1 pi before it becomes, because like it's undefined here and here, right? So it only works for a pi, then it's undefined, then it works for another pi, then it's undefined, then it works for a pi, and then it's undefined, and it keeps going around. So those are what we call the periods of those trig functions. So sine and cosine have a period of 2 pi. Tangent has a period of a single pi. So if we use that concept to evaluate without calculators the following trig functions, think of them as being periodic. So the sine of 2/3, and you know what? I think I just shut my calculator off too. So if I keep on doing coterminal angles, right, of 23 third pi, and keep subtracting 2 pi, subtracting 2 pi, subtracting 2 pi. And I want to show you a little trick. I don't know if your calculator has this or not, which kind of eliminates the math frac button. Oh, there we go. If I hit alpha, and then y equals, some calculators will do this, some won't on the TI-84s. I get my fraction options. So then I can do a 2/3 over 3, and then I can just keep subtracting 2, and it's going to give me my answer already in fraction form. That's kind of cool, right? So, oops, too many minuses. Minus 2, and I can keep on going. Oh, there, we hit it. So 5/3 pi. So sine of 23/3 pi really is just the same as sine of 5/3 pi. Of 5/3 pi. Okay, so 5/3 pi, now we have to think about where that would be on the unit circle. And since we're doing a sine, I'm looking for the y coordinate. Okay, so 5/3 pi puts us at, what, the 4th quadrant. Okay, so my fourth quadrant, my y is going to be negative, so I know that it's going to be a negative answer. So I think we're at 1/2 negative root 3 over 2. So my answer is negative root 3 over 2 on the unit circle. Cosine of 17/4 pi. So again, if I do that same thing, do 17/4 minus 2 minus 2 minus 2 minus 2 minus 2, as many as it needs me to get to between 0 and 2 pi's. That gets me to cosine of pi over 4. Okay, so that puts me in quadrant 1. That's at root 2, 2, root 2, 2. Okay, so then if we remember, cosine is, not that it really matters in this case, cosine is our x. So my answer is the square root of 2 over 2. Tangent of negative pi over 2. So if I keep adding 2 pi to that, so negative 9 over 2 plus 2 gets me at negative 1/2. So the tangent of negative 1/2 pi, so that gets me within that period of 0 to 2 pi, right? It's just we're going in the counterclockwise direction. So if we think about that, that's going to take me down here on my y-axis, which is the ordered pair of 0, negative 1. And tangent, remember our tangent is y over x. So my y is negative 1 over 0, which we can't have that. That's undefined. And then the sine of negative 29/6. So again, if I keep on adding 2 pi's to that, it's going to take me to the coterminal angle of negative 5 pi over 6. Okay, so negative 5 pi over 6. Remember sine, we're looking for our y. Negative 5 pi over 6 is going to probably get me to quadrant 3. Right, so everything's going to be negative, and then 5 pi over 6 gives me a reference angle of pi over 6, and that would be 30 degrees, right? Yeah, 30 divided by 180 is 1/6, yeah. So we're at 30 degrees, so that puts my ordered pair at root 3 over 2 and negative 1/2, because the opposite would be of my largest would be root 3. So my answer here is negative 1/2. Okay. All right, so periodic functions, and we can use the idea of them being periodic, which we kind of already had that idea with coterminal angles, right? To get to an angle or a radian that we're going to find within our unit circle. And then once you find that degree or that radian measure, then find the ordered pair that matches it, and then decide whether you're looking for the x or the y or a ratio of the x or the y's. Okay, so looking back at our ratios from example 1, can you name the reciprocal identities? So cosecant, we know, is the same as 1 over the sine of theta, which we've already talked about that, right? Which the sine is y, right? So 1 over y, so the same thing. I guess we already wrote that up there. Secant is the reciprocal of the cosine, so 1 over cosine theta. And cotangent is reciprocal of tangent, so 1 over tangent of theta. So then we can think about our tangent and cotangent in terms of sine and cosine, which we call the quotient identities. So the tangent would be y, which is sine over x, which is cosine theta, and the cotangent would be cosine theta over sine of theta, which I think we already knew that, but now we have it written down in our notes officially. Okay, so now we're going to get to some good blending of it all together. So when given the terminal point of an angle rotated on a coordinate plane, you should be able to create a right triangle by dropping a perpendicular line back to the x-axis and use the Pythagorean theorem to then find the hypotenuse. So for example 3, we're going to find the exact values of each of the 6 trig functions of an angle theta if negative 2, 5 is a point on the terminal side. So now we're no longer in just a unit circle. because our radius may not all be 1 now, which it won't be because we're at negative 2, 5, right? So that's not within the ranges that we were on before. So let's go ahead and recreate this. So negative 2, 5, I'm just going to eyeball it and call it right there. Negative 2, 5. If you want to be really precise about it, go for it, but you don't have to. So now I'm going to drop a perpendicular straight down to the x-axis, and then I'm going to make a diagonal hypotenuse down to the origin, and now I just created angle theta. Remember, your reference angle always is attached to the x-axis. Don't ever put it right here. So what would be the lengths of my legs? Well, my x is telling me I'm going to the left 2, so the length of it would actually be 2. I'm going up 5 on my y-axis, and then using the Pythagorean theorem, 25 plus 4 is 29, so that we get root 29 for my radius. So now we can use those to come up with my 6 trig functions evaluated at theta. So sine, remember, is opposite over hypotenuse, or just y. So in this, well, I guess it's y over our hypotenuse, right? So y over r, which is 5 over the square root of 29. Which if I were to rationalize that, 5 root 29 over 29. Cosine of theta is adjacent, so 2 over the hypotenuse, 29. So 2 root 29 over 29. Tangent of theta is opposite, so my opposite is 5 over adjacent, so 5/2. Oops, I'm forgetting something very, very important though. This really technically, because we are in quadrant 2, my cosine is going to need to be a negative 2, and I need to have a negative 2 down here on my tangent. So carry those signs with it, so negative 2. Carry the signs, carry the signs. Sorry, I did not do that. Because we need to have those ordered pairs to be following the signs of the quadrant that it lies in, right? Because if I had it as 5/2, then it would put it in quadrant 1. Or technically, I guess, quadrant 3 too. Tangent's positive in quadrant 3. Okay, so now let's do the reciprocals of those. And I'm running out of space. I can go over here. Get rid of that. Okay, so cosecant of theta is the reciprocal of sine, so root 29 over 5. Secant of theta is the reciprocal of cosine, so root 29 over negative 2. And cotangent of theta is the reciprocal of negative 5/2, so negative 2/5. Okay, so now we have all 6 trig functions evaluated for a ratio of a point with its terminal side, or point at negative 2, 5. Okay. All right, so example 4, now we're going to use our fundamental identities to solve out our trig functions. So given that the sine of theta is equal to 2 square roots of 3 all over 13, and because I see that, I'm going to rewrite this, because that really would probably be the same as 2 over the square root of 13, right? And this is probably the same as just 3 over the square root of 13, just rationalized. So I'm going to rewrite it like that because it's the most simplified, well, not the most simplified form, but it's going to make it easier when I make my hypotenuse the square root of 13, as opposed to 13 and then have to deal with the 2 root 13 everywhere else. Okay, so let's go ahead and create our right triangle. Because both sine and cosine were positive, that's going to put me in quadrant 1, because remember, all are positive. All students take calculus, so all of them are positive in quadrant 1. I'm going to make my reference triangle here. My hypotenuse is the square root of 13. Remember, sine is opposite, so that 2 is going to be opposite of my reference angle, and the 3 is going to be adjacent to it. Okay, so there's the setup. So now let's find all exact values of my 6 trig functions. So setting up the triangle is the hard part. Doing the rest is pretty easy. So the sine of theta is equal to 5 over the square root of 29, which is 5 root 29 over 29. which would make the cosecant of theta root 29 over 5. The cosine of theta is equal to, hold on, I'm on the wrong one. Sorry guys, you're probably thinking, what? I'm looking at the wrong triangle. I didn't even look over here. I'm too zoomed in. Let's try this again. The sine of theta, what are we looking for? The 4 remaining. We already have sine, we already have cosine. Ay, 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 it's Friday. Is it time to go home yet? So we did sine, we did cosine. Let's do the cosecant. So the cosecant of theta, so remember this was 2 over root 13, so it would be root 13 over 2. The secant of theta would be the reciprocal of 3 over root 13, so root 13 over 3. Now I'm back in action. The tangent of theta is equal to opposite over adjacent to 2 over 3, and my cotangent of theta would be reciprocal of that, so 3/2. Okay, I hope you really didn't start writing that stuff down. I apologize if you did. Okay, so now we're going to use these properties to find more exact values of each expression. So the tangent of 50 minus the sine of 50 over the cosine of 50. So whenever I see those ratios with sine and cosine in it, that should be kind of triggering this light bulb in my head to think, oh, that's just the same as the tangent of 50 degrees. And you should be able to go back and forth between those very easily. So we can make the tangent turn into a ratio of sine and cosines, and we can take a ratio of sine and cosines and take it to a tangent. Intermix those quite easily. So then the tangent of 50 degrees minus the tangent of 50 degrees is 0. 5b, I have the cosine of 40, or 400, times the secant of 40. Well, that's not quite in my head, so I'm going to do 400, find the coterminal angle, subtract 60 from that. That turns into cosine of 40 degrees, okay, times the secant of 40 degrees. Oh goodness, well what's the secant? Secant's the reciprocal of the cosine, so that's just the same as 1 over the cosine of 40 degrees times the cosine of 40 degrees. So what happens there, cancel, cancel, 1. So the cosine of 400 degrees times the secant of 40 degrees is just going to be 1. Isn't that fun? See, this is where the stuff gets good. So for 5c, we have sine of theta, or sine of pi over 6, that's good. Cosecant of 13 pi over 6. So if I keep subtracting 2 pi from that, that cosecant's going to turn into, I think just pi over 6 times the sine of pi over 6. Hopefully you can see where this is going. That's the reciprocal of 1 over sine pi over 6 times sine pi over 6. Cancels, cancels. 1. Okay. All right, so we did our reciprocal properties, we did our quotient properties. Now we're going to get into the Pythagorean theorem identities. I guess I should be saying identities, not properties. Okay, so if we again let P be some point x comma y on the unit circle that corresponds to the angle theta, then the equation in the unit circle we know is x squared plus y squared equals 1 squared, which in this case 1 squared is 1. Okay, so then we know that y is sine of theta, x is cosine of theta, so we can substitute these values, which gives us the equation of sine squared theta plus cosine squared theta is equal to 1. Okay, that's called our Pythagorean theorem identity. And then we can manipulate that and play around with that some more. Go away. So there are 2 more Pythagorean identities that we can then derive from there. So let's say we divide each side of that original equation by the cosine squared theta. So then we would get sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta is equal to 1 over cosine squared theta. And we can do that, right, because I'm dividing every single term in my equation by cosine squared theta, so it's keeping it balanced and equal. So this turns into what? Well, that's just the ratio of tangent. Isn't tangent y over x, sine over cosine? So that's the same as tangent squared theta the middle is just 1, and this is the same as secant squared theta. Okay, so that's just another variation of our Pythagorean identity. We can do the same thing and divide everything by the sine squared theta. So sine squared theta divided by sine squared theta plus cosine squared theta divided by sine squared theta is equal to 1 over sine squared theta. That gets me 1 plus, this is cotangent, right? Cosine over sine will be the reciprocal of sine, which is equal to, the reciprocal of sine is cosecant squared theta. Okay, so we can manipulate those like that and get us to those 3 Pythagorean theorem identities. As long as you remember the first one, you should easily be able to get to the other 2 just by dividing everything by sine squared or cosine squared. All right, so for our last example, we're going to use these identities. In example 6, it says, given that tangent of theta is equal to -1/2 and sine of theta is larger than 0, so that makes it positive, find the exact value of each of the remaining 5 trig functions. Okay, so we have our point P, make our reference angle. Okay, so theta is this whole entire angle, but we're going over -2, we're going up 1. 1 squared plus 2 squared is 5, so my radius is √5. Okay, I'm going to keep that negative there. Okay, and why do I know that? Because it was, so where do we get that point? Remember, tangent is opposite over adjacent, or y over x. And since it said my sine, I need it to be positive. Your sine is your y, so that made my y needing to be +1, which would make my x be -2. Or sorry, I didn't do that right. My y needed to be +1, my x needed to be -2. I said it right, but didn't write it right. That's where the -2, came from. I should have clarified that a little bit better. Okay, so now there's my triangle. Fill in the rest. So sine of theta is going to be √5 over 5, because 1 over √5 is √5. Yep, everybody's okay with that. Cosecant of theta would be just √5, because the reciprocal of 1 over √5 is √5. Cosine of theta, it would be -2 over √5. I guess I'll write it out this time. -2 √5 over 5. So my secant of theta would be √5 over -2. Tangent of theta would be equal to -1/2, which they told us, which would make cotangent of theta -2. All right. I hope you had much fun as I did. I don't know. I really enjoy this stuff, so I hope you do too. All right, that concludes your notes. Bye, guys.